All around the world there have been many different types of bridges constructed. They play a very important role in transportation for society. Bridges can be made for crossing over rivers, with roads or even railways. No matter how big or small the bridge is, it will always have to support its own weight and also the load that is applied to it after construction, such as vehicles or pedestrians. Bridges have been created for civilization for many years. Originally, bridges would be made out of the simplest materials and designs. Bridges then developed and allowed carrying of wide deckings and crossing of large distances over huge valleys, rivers, and even small streams, which enabled elevated surfaces strongly and pre-built city infrastructures. When more years go by, the more bridges are being constructed and have also become beautiful symbols for many different places. The engineers play huge roles for constructing bridges, and they have been the ones to create many different designs. Three main types of bridges that are considered to be able to handle types of natural forces are the beam bridge, the truss bridge, and the arc bridge. Technology is advancing when years proceed, resulting to more recently constructed bridges to be more advanced than others. For example, new bridges that have become popular are the cable-stayed bridge and suspension bridge. The main objective of these bridges is to ensure an outcome that will succeed for longer spans of lifetime. When constructing a bridge, there are forces that are considered to make sure the bridge will handle the weight from society and nature. When there is an external force on a structure, it creates an internal force. The five most common types of internal forces include tension, compression, bending, shear, and torsion. Travel and exploration has changed during the years of structural development to enable reduced time, tools, and aid when traveling. Bridges can vary in their appearance, capacity, structural elements, and construction materials. They will be able to serve various roles, different types of weight and size. The simplest form that contain horizontal beams are called beam bridges. They can travel to a large length and area that spans between abutments, which relieve pressure of the structural piers. The main force which impacts the beam bridge is the alteration of vertical forces, which is then transferred into shear and flexural load and used to support the structures. Due to simplicity of beam bridges, they are the oldest bridge constructed in history. Historically, bridges were initially built using wooden logs over short rivers and lakes. These bridges were used substantially when metal, steel, and concrete was first used as a material supply.
A brief description of the bridge design we had chosen and the reasons behind why we chose to construct the bridge as we did. When a bridge is to span between two separate bits of land, such as over valleys, rivers, and even small streams, the common choice to create access over the top is a beam bridge. Out of all the bridge types, the beam bridge is known to be one of the simplest bridge types, making it perfect for our construction capabilities and our small amount of resources. This is due to the design and type of engineering that is considered during construction. During modern advances in engineering, the beam bridges have undergone extensive development and its design has been incorporated in the construction of some great structures. Due to these beam bridges not have been used regularly across the world, their design has been altered into other modern bridges. When thinking of creating a bridge, we discussed strength over every asset. Therefore, the bridge design we chose was a beam bridge, as my group had discussed that we thought it would be the strongest design. We still wanted to make a bridge that would look presentable while trying to make it strong. When we had decided on what bridge we wanted to create, we found inspiration from the Manic Swamp Bridge, which is located in Louisiana, United States of America, where the flat design and beams which would hold the bridge up were incorporated into its design. We had a perfect idea to then put small beams vertically across the insides of the bridges to help support the weight on the thick, flat base bridge. in order to distribute the weight vertically along the spaghetti in order to hold more weight ultimately. Although when constructing the bridge, we had made the base by placing 3 layers of spaghetti over each other to create a thick base, then when it came to creating the beams for the bridge, we had already used too much spaghetti and had exceeded the weight limit. To work around this problem, we reduced the amount of spaghetti used in further construction in order to not further exceed the weight limit. One mistake that we made as a group was underestimating the weight of the glue when being used in such large quantities, which also led to the further exceeding of the weight limit.
The bridge was constructed using only spaghetti and Shelley's quick super glue, as specified on the task sheet. Using these items, our group was able to construct a bridge which had been planned to look and work like its real-life example, which was a swamp bridge. The design is simplistic as it consists only of the base road of the bridge, concrete columns underneath, and concrete bollards on both of the sides in order to keep objects traveling across the bridge on it. In our design, we made the base bi-layer with solid interlocking panels in the middle to give it a more ability to flex instead of snapping immediately. Superglue was applied to hold all of the spaghetti together, and extra amounts were added to the middle interlocking plates. After allowing the superglue to dry, triangular shapes were added to the bottom of the bridge. This was done as triangles are very strong and durable shape, which would allow the bridge to take on more weight. This was done by putting poles of spaghetti approximately 5 strands thick underneath the bridge in a zigzag shape. Next was the bollards, which we put on either side, then glued. Putting in a middle bollard was considered, but we already exceeded the maximum weight and wanted to keep this to a minimum. 2 bridges were made this way and one was tested at home. Without measurement though, as we did not know how to measure the downward forces as accurately as the machine used for the official testing. The test bridge did not perform as well as we had expected, so more superglue was added to the official bridge in hopes that it would fortify and make the bridge more durable. A quick analysis of how the bridge was made shows that if more strength was needed, trusses could have been added, but our group did struggle making the trusses. More interlocking plates could have been added instead of having one flat plate. Having many in a zigzag type pattern may have proved more successful, and more support up the top, like the triangles on the bottom, would have provided the bridge with much more structural security than the bridge had.